Hello students, good day. My name is Iron Joy H. Fernandez and I will be your teacher in Abstract Algebra. Today, we are going to discuss a new topic, and that topic is the introduction to group. This topic aims to define group and abelian group, identify if the set of elements are group or not group, and identify if the group is an abelian or non-abelian. But before we start, let me ask this question. Who were the mathematicians behind this group theory? In 1882, Weber, Bondic, and Heinrich Weber independently gave clear definition of an abstract algebra for the first time. However, long before the development of group theory, there are numbers of such integers, rational numbers, real numbers, and complex numbers which form natural groups, rings, or fields under the operation of the usual addition and multiplication. This algebraic structure of numbers are employed as axioms for abstract groups, rings, and fields. Walter Bondic and Heinrich Weber are the ones who were responsible of knowing the algebraic properties of the definition of the group. However, the term group was because of Évariste Galois. In 1854, Évariste Galois gives the first abstract definition of the groups. Galois is honored as the first mathematician linking the group theory and field theory with a theory that is now called Galois theory. Now let's define the group. What is a group? A group consists of a non-empty set G together with a binary operation star or asterisk such that the following properties hold. What are these properties? These properties are the closure, associativity, identity, and inverses. Now, what is closure? Closure says that if you take any two elements in the set G and apply the binary operation, then A star B should also in the set G. How about associativity? That's the one where you move the parentheses around. And since we're not talking about addition or multiplication, we're just talking about our general binary operation star, we can say that A star the quantity B star C is the same as the quantity A star B star C. Then we have the identity. What is identity? There's some element in this set and we are going to call that element E. The letter E is typically what people use when they are talking about identities in general. In identity element, there exists an element E in the non-empty set G, such that for every A that is an element of G, A star E is equal to E star A is equal to A. That means that if you apply element E with a binary operation to any A that's in G, the result would be that element A itself. Lastly, we have inverses. For any element A that's in the set G, there exists an element and we're going to call it A inverse or the inverse of A that's also in the set G, such that A star A inverse equals A inverse star A equals the identity, which in this case would be E. And that's it. That's the definition of a group. Now, what if the group is commutative? There's another term in group theory that is famous, and it is named after Niels Heinrich Abel from 1802 to 1829. This group is called abelian. The group G is called abelian if its binary operation is commutative such that A star B equals B star A for all elements A and B. Abelian is also known as commutative. Since we already know the definition of a group and the abelian group, now let's take a look at some example. Determine if the following are groups or not, and prove if it is an abelian or non-abelian. For the first example, suppose we have integers under addition. Is this a group? For the first property, closure, we know that integers under addition satisfies the closure identity. If you take any two elements in the set Z and apply the binary operation, then A star B should also in the set Z. For example, 1 plus 3 is equal to 4, that is an element of z. 4 plus negative 1 is equal to 3, which is also an element of z. So yes for closure. For the second property, is it associative? Of course yes. To verify, let's take a look at this example. A plus the quantity B plus C equals the quantity A plus B plus C if A is equal to 1, B is equal to 2, and C is equal to 3, then 1 plus the quantity 2 plus 3 equals the quantity 1 plus 2 plus 3. By associative property, we got 6 equals 6. So we can say that it is associative. For identity, it is known that 0 is the additive identity E on the set of integers z, since for all A are elements of integers z. For example, A plus 0 equals 0 plus A equals A. If A is equal to 4, then 4 plus 0 equals 0 plus 4 equals 4. So we can say that yes, z under addition holds the identity property. Lastly is the inverse property. For any A that's in the set of integers z, there exists an element A inverse that's in z. For example, on z under addition, it is known that negative A is the additive inverse of A. So we can say that A plus negative A equals negative A plus A equals identity element A. If A is equal to 2, then 2 plus negative 2 equals negative 2 plus 2 equals 0. So we can say that yes, it satisfies the inverse property. Since z under addition holds these 4 properties, therefore z under addition is a group. Now let's prove if this group is an abelian or non-abelian. As what I've said earlier, abelian is also known as commutative. So that means that a group is abelian if it is commutative. Under commutative property, z under addition is known to be commutative. Yes, it is commutative. Here's an example to prove that it is true. A star B equals B star A for all AB elements of z. Under addition, we have A plus B equals B plus A. If A is equal to 2 and B is equal to 3, then 2 plus 3 is equal to 3 plus 2. Since the group satisfies the commutative property, then it is an abelian group. Now let's proceed to the next example. For the second example, suppose we have integers under multiplication. Is this a group? For the first property, closure, we know that integers under multiplication satisfies the closure identity. If you take any two elements in the set Z and apply the binary operation, then A times B should also be in the set Z. For example, 2 times 4 is 8, which is element of Z. 4 times negative 1 is equal to negative 4, which is also element of Z. So yes for closure. For the second property, associative, is it associative? Of course yes. To verify, let's take a look at this example. A times the quantity B times C equals the quantity A times B times C. If A is equal to 2, B is equal to 4, C is equal to 5, then 2 times the quantity 4 times 5 equals the quantity 2 times 4 times 5 equals 40. So we can say that it is associative. For identity, it is known that 1 is the multiplicative identity E on the set of integers Z, since for all A are elements of integer Z. For example, A times 1 is equal to 1 times A equals A. If A is equal to 5, then 5 times 1 equals 1 times 5 equals 5. So we can say that, yes, under multiplication, Z holds the identity property. We have already proven that the elements of Z under multiplication holds the first three properties: the closure property, the associative property, and the identity property. Now, let's try if it also satisfies the last property, which is the inverse. In inverse property, on Z under multiplication, it is known that A raised to negative 1 is the multiplicative inverse of A. So we can say that A times A inverse equals A inverse times A equals the identity element E, which is equal to 1. Or we can write it as A multiplied by 1 over A equals 1. In this example, we have to do two cases to prove that it satisfies the property. Case 1. If A is equal to 1 and A is equal to negative 1, then 1 and negative 1 are the multiplicative inverses respectively. Example, we have 1 times 1 over 1 equals 1, and negative 1 times 1 over negative 1 is equal to 1. So it satisfies the property. However, in case 2, if A is not equal to negative 1 and 1, let's say for example that A is equal to 3, then A multiplied by 1 over 3 is equal to 1. But the problem here is 1/3 is not an integer. Or if you consider 2, then 2 multiplied by 1/2 equals 1, but 1/2 is also not an integer. Or if you apply A is equal to 0, then it is also not applicable. So in this case, only 1 and negative 1 have multiplicative inverses. Therefore, this set does not satisfy the inverse property. In this example, we have proven that the set of integers under multiplication holds the first three properties: the closure property, associative property, and the identity property. However, it does not satisfy the last property, which is the inverses. Therefore, the set of elements Z under multiplication is not a group. That ends our proper lesson for the introduction of a group and abelian group. In this lesson, we learned that a group consists of a non-empty set G together with a binary operation star such that the following properties hold. Such properties are closure property, associativity, identity property, and inverses. Groups are not required to be commutative, and if a group G satisfies the commutative property, we call that group an abelian group or commutative group. Otherwise, it is called non-abelian. Now that everything is clear, you are now ready to put it to practice. What have you learned from our previous activities and discussion? In this task, you are going to identify if the given set of elements is a group or not group. If it is a group, then tell whether a group is an abelian or non-abelian. Remember, to be a group, you have to satisfy the four properties: the closure property, associativity, the identity element, and the inverses. And to be an abelian, the set of elements must hold the commutative property. You have 10 seconds before giving your answer. Are you ready? Good. Let's start number 1. The set of real numbers under addition. Is it a group? The correct answer is yes. Well, we know that the real numbers under addition satisfy closure, associativity, identity, and inverses. In fact, we know that under addition, we can say that it is associative. We can say that the identity elements of real numbers under addition is 0. We can also say that the additive inverse of element A is negative A. So we conclude that yes, it is a group. And for commutative, the set of real numbers under addition is commutative. If A and B are two rational numbers, example, if A is equal to 2 over 5 and B is equal to 3 over 7, then A plus B equals B plus A. By commutative property, would give us 2 over 5 plus 3 over 7 equals 3 over 7 plus 2 over 5, which is equal to 6 over 35 equals 6 over 35. And so, it satisfies the commutative property. Therefore, the group of rational numbers under addition is an abelian group. The set of integers under subtraction, is it a group? The correct answer is no, it is not a group. Let's try to prove that it is not a group. For closure, when you subtract b from a, you get c. When you subtract two integers, you get another integer c. And that integer c is also in the set. So we can say that yes, for closure, it satisfies the closure identity. But for associativity, is the quantity a minus b minus c the same as subtracting a minus the quantity b minus c? No. For example, if a is equal to 1, b is equal to 2, and c is equal to 3, then the quantity 1 minus 2 minus 3 equals 1 minus the quantity 2 minus 3. By associative property, we get negative 4 is not equal to 2. If you notice, negative 4 is not equal to 2. Therefore, the set of integers z under subtraction is not a group. Notice also that this set is closed but does not have an identity and therefore also does not have the inverse property. Number 3. The set of rational numbers with the element 0 removed under multiplication. Is it a group? The correct answer is yes. We have already seen that the set of rational numbers with the element 0 removed under the operation of multiplication is closed, associative, have identity element 1, and that any integer x has the inverse 1 over x. Because the set of rational numbers with the element 0 removed under multiplication satisfies all four group properties. Therefore, the set of rational numbers with the element 0 removed under multiplication is a group. Now, to prove if it's abelian, consider the set of rational numbers q that is in the set of numbers a over b such that a and b are integers and b is non-zero, and the operation multiplication, since the rational number 0 does not have a multiplicative inverse, that means it is not a group. However, if we instead use the set q asterisk instead of q that includes every rational number except 0, then q asterisk under multiplication does form an abelian group. Example, by commutative property, a times b equals b times a. If a is equal to 1/2 and b is equal to 3/4, then 3/8 is equal to 3/8. That ends our first activity. Did you get all the answers correctly? Congratulations for a job well done. To further enhance your learning, here is another test. Instruction: identify if the following representation are group or not. And second, identify if a group is abelian or non-abelian. Prove your answer. You're only given 10 minutes to answer this activity. Minutes is over. Were you able to answer all the items correctly? Congratulations for a job well done. That ends our lesson for today. Again, I am Iron Joy H. Fernandez, your teacher in Abstract Algebra. Thank you and keep safe. Goodbye.